Welcome to the data science lecture. My name is Henrik Hoyer and I'm your lecturer. I have a Masters of Science from the Royal Institute of Technology in Stockholm and Aalto University in Helsinki, and a Bachelor of Science in Digital Media from the University of Bremen, and I'm currently a research scientist at the University of Bremen. Before that, I worked as a research scientist at the University of Amsterdam. And I would like to start this lecture with this schematic of what data science is. And you can see in this Venn diagram that we have these three big blocks. We have mathematics and statistics, we have domain knowledge, and we have hacking skills. And as you can see, this combination of mathematics and statistics and domain knowledge about a particular field, let's say biology or sociology, is what's happening. It's what's usually happening in traditional research. The combination of hacking skills, that is technical skills, and mathematics and statistics, it's what's commonly happening in machine learning. And in this data science course, the idea is to combine the three, to have a background in mathematics and statistics, to combine that with our hacking skills, with our technical abilities, and to combine that with domain knowledge. And that, in a way, is what data science is all about for me. I would like to start this lecture with this example from a book about the possibilities of artificial intelligence. We will learn that machine learning is a subset of artificial intelligence, so don't be confused if it says artificial intelligence in this text, but let's read it out. While many areas of human endeavor have currently seemed to flounder, such as understanding and dealing with economic systems or correcting social injustices, research and technical developments in the scientific field of artificial intelligence have exploded. As a result, artificial intelligence researchers are developing computers that can listen to spoken sentences and grasp their meaning, that can read news stories and write succinct, accurate grammatical summaries, that employ robots who never get bored to work on assembly lines, that assemble data about a sick person and suggest a diagnosis. And I would like you to stop the video to think a bit about when this was written. Was this written in the 60s? Was this written yesterday? Was this written, I don't know how many years ago? So this was actually written in the 1980s, a time when many of you weren't born. I wasn't born either. So it's quite old. But what you can see if you look at the news and how artificial intelligence and machine learning are discussed nowadays is that a lot of these promises, a lot of these advancements are still kind of recent or feel kind of recent. And that's something that we will see again and again. We have technical abilities which can be very, very impressive, but at the same time also quite limited. What you will learn in this course is to distinguish the two, to see the possibilities and to also see the limitations of these approaches. I'd like to start with this paper. It's by Michael Kosinski and others, and the paper is called Private Traits and Attributes are Predictable from Digital Records of Human Behavior. What we're talking about here are Facebook likes, that are the digital records of human behavior that we consider. This was a famous paper in which they showed a relationship between what people like on Facebook and private traits and attributes about them. And I'm going to show you this on the one hand to enable you to understand what is possible to learn from data, how much we can actually infer from the digital records about human behavior. And on the other hand, because this is really the paper at the heart of the Facebook Cambridge Analytica scandal that we will talk a bit about in this lecture as well. But first, let's consider how much can actually be predicted from data. And the idea here is to turn it a bit into a quiz. It's of course not so interactive in a video, but what I'd like you to think about is to see this attribute, and that's Harley Davidson. It's somebody liking Harley Davidson on Facebook, and to consider what this might be able to predict. What can you predict from this? So again, maybe pause the video, think a bit about, okay, what likes would Harley-Davidson be predictive on about a person? And the solution here is that it's low intelligence. The researchers, Michael Kosinski and others, found a correlation, a relationship between people who liked Harley-Davidson and people who had low intelligence. We continue the quiz here a bit, not judging about Harley-Davidson at all, and consider what this picture, and this what we're depicting here are curly fries, a particular kind of French fries, what these curly fries are predictable of. Now again, consider what could this be predictive of? And we find that this is predictive of high intelligence. And this is interesting in two ways. On the one hand, there seems to be a relationship in the data. On the other hand, it feels quite random, right? Why would liking something like French fries actually tell us about the intelligence of a person? But we see that a lot, and there's a lot of correlations in the data. Some are causal, many of them are not, and we have to explore this more and more to get better data scientists and to actually make predictions about the future that are generalizable. Because that's our goal, right? To make predictions about the future that we can generalize. Other things that are highly correlated with French fries are, for instance, thunderstorms, the Colbert Report, and science as a whole. One final example, here we have the musical Wicked, and that was found to be predictive of homosexuality. So again, we have a setting here where we take the likes of some people, all the things they've liked, and we predict certain attributes about them, their sexual orientation, and their intelligence. And we find these correlations, we find that certain things are predictive about certain things. And this can be done for a variety of other things. And here we have a data set, and this is still the paper by Michael Kosinski and others, where we have 58,000 volunteers who provided Facebook likes. And we can make a lot of predictions with quite high accuracy. We can, for instance, distinguish whether somebody is Caucasian or African American. And we can also distinguish whether somebody is male or female with quite high accuracy. We see that sexual orientation can be predicted with high accuracy, as well as political orientation in the binary American system. There's also the possibility to distinguish the religion and to make some estimate about drugs. You notice that here the substance abuse, whether somebody did drugs or not, can be predicted with 65 to 73% accuracy. So it's not as high as, for instance, distinguishing the gender of a person, but it's still quite high. And in the paper, they have another example that's quite interesting. They try to predict whether your parents, the parents of a person, were separated before the 21st birthday of a person. And here again, we have 60% accuracy. Now, think about that. Just randomly guessing, just saying they were separated or not, would be 50%. You would flip a coin, right? You have two classes, so it's either this or that, so it's 50% chance if it's completely random. That means that there's some indication in the data, but that still might be misleading. And this is an important skill that we have to learn in this class, right? To get a feeling of when do we actually learn something, or when are we dealing with spurious correlations. We will also think about what this means from a discrimination perspective, right? We saw that homosexuality can be predicted from the likes of a person, so people who want to discriminate against other people can actually use that for their purposes. And this is not a hypothetical problem. This is already happening. This is happening in the housing market. This is happening in the job market, where certain attributes about a person are used to make predictions about him or her and to make decisions about him or her, and often to discriminate against certain people they don't want. So what you see here is a positive result of a pregnancy test. And there's quite an interesting story behind this, because Target, which is one of the big shops, supermarkets in the United States, they figured out that a person was pregnant before she knew it herself. They looked at her purchasing history and tried to provide targeted ads, tried to give her coupons to make her buy more and more things, and they started recommending her things related to pregnancy. And then people, especially her father, as the story is told in the news media, got very angry at Target that they would recommend things related to pregnancy to his teen daughter. But it turned out that she was actually pregnant, and that Target just saw that already based on her purchasing history. So the father had to excuse himself. And the question here, and why I bring this up in this course, is of course what this means about teen pregnancy, right? What does this mean for women in a culture where it might not be allowed to have a child without being married, right? We have all this data and we can learn a lot about the person from the data and from his or her digital traces. And the question is, of course, what does this mean and how can we control this? And here's just another example, just how much can be inferred from the data, even just so-called metadata. This is my social network. So there's a website on immersion.media.mit.edu with which you can import all your data and then can see who you're writing emails with, right? And then it's looking for patterns in the data to find how many people you share a lot of emails with, like the bigger the circles, the more emails you exchange with the people, and who is part of a conversation if you have more than one person that you're emailing. And what you can see quite nicely here is that you have in blue my family, and you have different circles of friends that I connected with. You can learn a lot about a person just from this metadata, and it's really without looking at any of the affiliation of the people. It's just the actions of the people, just what's in the data. And we will look a lot about this. But first, let's consider some more examples of machine learning. One of the classical examples is spam filtering, and I'm pretty sure that each one of you uses that already. But think about that. You just have an email and you make this decision whether this is an appropriate email, an email I would like to receive, or spam, unwanted email. It's quite impressive that this can be done with the current technical means, and we will learn in this lecture that we're very far from text understanding, but that we can still make that decision. Machine learning is also applied in all kinds of biology. It's also applied, for instance, to recognize handwritten numbers, to recognize text and images. You probably all know about the promises of self-driving cars. So far, they don't exist as a consumer product that you can actually use. But that's another example where machine learning techniques, computer vision techniques predominantly are used to give computers the ability to do things that humans normally would be doing. There's also recommendation systems as one important subset of machine learning techniques. And we will look at this quite a bit because it's one of my research interests and because a lot of people are interacting with machine learning systems through recommender systems that may or may not be aware that such systems exist at all. And then there's many, many more examples. Here on the bottom right, you see a system that takes an image and automatically translate that image into text. So take an image and you describe the image. We're going to explore that a bit in our lecture as well. Another example from autonomous driving would be the detection of other cars. And again, you're all programmers if you take this course. Think about how you would do this with a normal programming language, right? With if, then, else statements. How would you code a system that can see this is a car, and this is a cat, and this is a tree? It's quite challenging, but we will learn in this course how that's possible, how this can be implemented using machine learning. There are some other examples, for instance, the recognition of faces, the generation of music, and machine translation, for instance, where you take one language, for instance French, and automatically translate it into English. Let's formally define data science or operationalize it for this lecture. For the purposes of this lecture, I consider data science or anything related to data science as the application of computational and statistical techniques to address or gain insight into some real-world problem. That of course poses the question, like, how is this different from machine learning? Well, I would say that machine learning is focused on the algorithm. It's on the focus of machine learning as a research discipline is about advancing algorithms to build better algorithms, whereas in data science we want to apply this to answer certain questions. And that we think, therefore, data science is more or less applied machine learning. Right? Data science takes domain knowledge into account to answer real-world questions. So let's formally define machine learning. Machine learning, according to Samuel, is the field that gives computers the ability to learn without being explicitly programmed. And as you can see, it's quite an old definition, but it's one that's still used a lot. And of course, it's nice because you have this not explicitly programmed in there, whereas in a classical fashion, you say, if A equals B, then do this, while you have all these programming statements. Here, you do not explicitly program it, but you set up a metric, set up some optimization goal, and then you optimize the system statistically. We're going to learn a lot what this means. We're going to focus on this in much more detail, but let's also consider a downside of this definition. And the downside, of course, is that we have machine learning here defined with using the word learn. And that can be quite confusing because with like this definition still leaves it open what it actually means to learn something. Here's a more explicit definition of machine learning that considers machine learning as a computer program that learns from an experience E with respect to some class of task T and performance measure P if the performance at the tasks as measured by the performance measure improves with experience E. So let's say, for instance, the goal is to detect, is this a spam email or not? Then we could look at how many of the emails we correctly predicted and how many we misclassified and make changes to our model. And if then, over time, with experience, our performance at predicting is this spam or not improves, then we can say we have a machine learning solution here. Now let's talk a bit about the bigger picture. As I said, machine learning is a subset of artificial intelligence. And artificial intelligence as a term is even harder to define than machine learning. There are some definitions that call it machine, that say that AI is whatever hasn't been done yet. Well, formally, I would define artificial intelligence as any kind of software or hardware that gives computers the abilities that are normally subscribed to humans. So whenever we have something that a human does and we implement it in a machine, we can call this artificial intelligence. For the purposes of this lecture, I will mostly talk about machine learning, and I will use the terms artificial intelligence and machine learning synonymously. There's also the term deep learning, which is very popular in the media because it gave us some of the advances that we will talk about in this lectures in relation to computer vision, that is the detection of objects in images, and translation, for instance, going from English to French. But it's only a small subset, and the primary focus of this lecture will be machine learning as a whole, mostly focused on simpler, more explainable machine learning techniques than deep learning. There's also the so-called good old-fashioned AI, which you might have encountered in books like Gödel, Escher, Bach by Douglas Hofstadter. That's a logic-based approach to artificial intelligence that was very popular from the 60s till the 90s. We won't do much on that. It's very interesting, very interesting. It's a very interesting field, but we can't focus, or we won't focus on this. Let's also quickly consider the difference of our approach to statistics. Statistics as a discipline is very much focused on explanations. It's more theoretical and mathematical, whereas we in data science focus on practical problems, and we have to deal with things like data scraping and data transformation, and that makes this lecture very different from a statistics lecture that you could be taking. Let's consider some nomenclature. That's important terms that I will use throughout the lecture. We make an important distinction between the so-called features and classes. The features are sometimes also called attributes or dimensions, and that's basically what we make the predictions on in supervised machine learning tasks. For instance, here a possible task would be predicting what kind of flower this is, and we have the sepal length, the sepal width, the petal length, and the petal width, and we know what kind of flower this is. And so we have the features, and that's all the information that we have about the flower. It's the length and the width. And we have the classes. That is, what kind of flower is this? Each individual flower that we have in a data set, we call an instance. Sometimes this is also called a sample or an observation. We will revisit this throughout the course, but just make sure that you remember that instances are individual data points, right? Like data points that we can use for our prediction. Then we have the features, that's basically our X, that's what we're predicting from. And then we have the classes, which is our Y, that's what we're predicting. Now, also important to the study of data science is big data. We're different from big data because data science can also be done with much smaller data. So it's not strictly necessary, but it's still something that really makes a lot of things a lot easier and a lot more expressive. And if you look at the figure here, you find that there's really a lot happening in 1 internet minute. Right? There's 1 million logins on Facebook, there's 3.8 million searches, there's 700,000 hours watched on Netflix, and many, many other kinds of data created, as you can see here. And all this data, of course, can be analyzed in the same fashion as we analyzed the Facebook likes before. So we can learn a lot about people and society through these means. Games are quite important to artificial intelligence and the development of many of the techniques. And the two big milestones in regards to artificial intelligence was IBM, who beat chess in 1997, and Google, who beat the game Go in 2016. And why is this interesting? Because back in the day, people thought if we can have a computer that can play chess, if it's at that level, then we have human intelligence. Then we have really intelligent machines. And looking at the timeline here is that in '68, we have the international master David Levy, who bet that no computer will defeat him. He won his bet. But then 10 years later, after he won his bet, the first computer defeat a grandmaster. It still lost to Levy, one of the international masters. But then, not even 10 years later, we actually have a machine that beat the world champion Garry Kasparov at the time. And in 2016, and that's not so long after the first time a computer won against a chess grandmaster, we have no human that can play against the best computers. So we can see this, but what we also find is that we don't have intelligent machines yet, right? So actually, solving the game chess did not solve intelligent machines at all. And people were soon to realize that. They were saying, well, it's not artificial intelligence, it's just clever engineering. And we can also see this again and again in the history of artificial intelligence. As soon as something is solved, it becomes uninteresting, and people basically just say, well, yeah, we know how to do that. That's just clever engineering, but that's not artificial intelligence. So artificial intelligence and machine learning, to some extent, remain moving targets. They change all the time. And here we have the timeline for Go. Again, there was a bet. The bet was won. And then not so late after, there was an automatic machine that, again, through clever engineering, through a good combination of different machine learning techniques, beat the world champion Lee Sedol. Let's talk about self-driving cars. Again, also one of the most visible, most promising, probably also most exciting examples of machine learning and artificial intelligence. Here we see the car by the Stanford University, which won a DARPA challenge by navigating through a desert. This was one of the first cars that really was acting autonomously in a desert with a lot of different obstacles. Here again, we have a nice example of something that is looking quite powerful, that is working extremely well in research settings, even in big challenges that are run by big organizations, but still we don't have self-driving cars yet. So there's still a gap between how well these techniques work in the experimental settings, in the laboratory, let's say, and how well they work in practice. Here's another example of the application of machine learning in medicine, where it can be used to make predictions, to help doctors to read images and to understand medical records. One example from IBM, for instance, looked at glaucoma, which is the second leading cause of blindness. And it's a big problem because half of the cases go undetected, and they built a system to detect glaucoma using 88,000 retina images. So again, we have a lot of data here, and we know these are cases that have this disease, these are cases who don't have the disease, and then we make a prediction and a system that can assist doctors. Won't replace them, it can only assist them. Yeah, chatbots are another example. You know Siri, you know Alexa. They also use machine learning techniques to make these predictions. And as I said before, YouTube and other platforms use recommendations and machine learning systems increasingly to make the recommendations on their platform. And that comes with a lot of interesting questions, because we could have a situation here now where machine learning systems are influencing people. And we will talk and think about this a lot in this course. And one article I recommend you to write is called YouTube's Product Chief on Online Radicalization and Algorithmic Rabbit Holes. And the idea here is that you have the recommendation system on YouTube, and 70% of the videos watched on YouTube are recommended by this algorithm. And a lot of researchers are saying that, or like a lot of scientists and journalists are afraid that these systems could be radicalizing users by showing them content that aligns well with their prior beliefs and leads them to more and more extreme beliefs about certain issues. An example, also an article here in the New York Times, shows that in the Chemnitz protest some years ago, that this could have happened. Right? People who wanted to inform themselves about a political topic, that is, why people are protesting in Chemnitz, were shown more and more conspiracy, far-right videos, and were dragged down a rabbit hole of radicalizing content that then fueled the protest. And then we have a dangerous feedback loop here. So we will also consider this. What are the implications of systems that learn from data, from systems that take feedback into account? And there will be an exercise on that, but more on that later. But just so you understand what I'm talking about, each video on YouTube has a variety of recommendations, and there's a machine learning based system in the background that is selecting the different videos, because there's many hours of videos, and finding these selections by hand would be impossible. So they have this algorithm which is matching videos, like here a football video, which is matched to other football videos. And of course, this is important for advertising as well. They use this to also find the right ads for the right people, whatever that may be. Another example is speech recognition, where we take waveforms, audio data into a neural network, machine learning based system that then automatically converts that into text. And as you can see here are results by Google Research from Jeff Dean, who showed that deep learning in particular reduced the word errors of such techniques by more than 30%. The photo search on Google Photos is also powered by such techniques. Again, we have a picture and we classify the picture, and for instance for this picture the system automatically recognizes that it's about the ocean. Smart Reply is another example. Interestingly, it was launched as an April Fool's Day joke, but then turned into a real product some years later, and a year after it was launched, it was already responsible for more than 10% of mobile inbox replies. So what's happening here, you get an email and it automatically recommends 3 different responses, 3 different quick responses based on the content, understanding what the email is saying. And this, of course, is happening through data. It's made possible through data. And I really like this example to showcase the power of data. What you see here is, of course, what it looks like, at least, the map of Europe. But this wasn't taken from a geography book. These are just posts on a website that are geotagged, right? So Flickr was a photo sharing website on which people could upload their photos and indicate the location. And they took the data from Flickr with all the geolocation information and just plotted it on a canvas based on the latitude and longitude associated with the picture. And what you can see here is that a map of Europe emerges. You also see that certain parts like Amsterdam and London have a lot more data points than parts in Eastern Europe, for example. But still, there's a lot of information in the data that is invisible if you look at individual data points, but if you take them in a combination, if you visualize them right, and if you process the data right, you can make evident. So here's another example from business science. So this is what a business visualization system could look like. This is an advertisement from Microsoft. And as you can see, here are different ways of dealing with data, visualizing the data that can then be used to learn and answer real-world questions. And in a way, that's the goal of this data science course. Yeah, one important thing to consider in the context of machine learning is that there's no free lunch. And what this means is that no model works best for all possible situations. Because our models, the machine learning models we're dealing with, are always a simplification of reality. It's a simplification that is based on certain assumptions. That's a so-called modeling bias. But such assumptions can fail in certain situations. So we have to be thoughtful and we have to make a lot of compromise. We have to make a lot of decisions, justified decisions for which we have to provide reasons, but these decisions have a strong impact on the quality of our models, and we will learn in this course on how to make these compromises and how to develop systems that are actually good at making generalizable predictions. We will use a machine learning library called scikit-learn, which is very nice because this has an application programming interface that's very exchangeable, so we can try out a lot of different machine learning systems without much effort and without re-implementing the systems ourselves. It's a library that's used in a variety of contexts, for instance at Spotify, at INRIA, at Evernote, and many, many more by now. So you can use these also in your future work when you're working in a company as a computer scientist. And it's quite nice because it also has this nice cheat sheet, which helps you which guides you through the possibilities that exist for the different data that you have. And you can see they make an important distinction between labeled data and unlabeled data, and whether we're predicting a class or a quantity, or whether we're just looking at structure. And we will revisit this again and again. And we're going to learn about these different tasks that are outlined here. There will be a lecture on classification. There will be one on regression, one on clustering, and one on dimensionality reduction, so that you have a good overview on the different types of tasks associated with machine learning. Just quickly, let's also consider who hires data scientists, where are they working. You see that there is a nice increase in terms of data science related jobs. So I suppose it's a good time to learn about data science. A lot of big companies that you know already employ data scientists, especially Google, but also Spotify, Uber, or the New York Times. And there's a large number of industries that is interested in data science and data scientists. Among them are logistics, commerce, manufacturing, finance, but also journalism, people working on smart cities, people doing things like sport analytics.